Okay, so now we're recording the third video of our logarithmic functions lesson, and we're going to talk about using inverse properties and functions, and that's going to eventually lead us into how we graph. Now remember that when we are using inverse properties, we're having to take some stuff that we know and flip it around. Now I wouldn't really say that this is inverse properties per se. It kind of gets its name from the idea that how a logarithmic function comes into being and some shortcuts with it. So here's a scenario where, again, on that note card I told you about in the first lesson, you may want to put this and this. Put both of these properties, because when you see these scenarios, you're going to use them to help simplify your solutions. The first question says, simplify 10 to the power of log of 9 6/10. Thinking to yourself, oh my goodness, I could use my calculator to solve it, but if I use a little bit of mental math, maybe it won't be as necessary. So this formula is the same thing as saying b to the log of b of x, how all of that would equal just x. Remember that when we have a log function listed that doesn't have a base, that means the base is 10. So this is really 10 to the log of base 10 of 9.6. So here's our base, here's our log to that base, and here's our x value. So all of this would simplify to 9.6. You can also check this out, since it is a base 10 function. You could plug this into your calculator, 10 to the power of log, and then in parentheses again, 9.6. And simplify it out, and you're going to see that it equals 9.6. All right, example B. Noticing here that this time it's the logarithmic function. So we have log of 7, base 7, of 49 to the power of 2x. We're thinking to ourselves, okay, well the base is 7, but 49 isn't 7. So we have to think about some properties of 49. An equivalent way of rewriting that is to say that 49 is the same thing as 7 squared. So now, suddenly I have a base of 7. So the base of this power. Simplify this using our exponent property, power of powers. And so 7 to the 4x. We're going to multiply 2 times 2x. So now, here's my base. Here's the similar base, and to the x power, so that means x is equal to 4x. So now I've simplified it so that all I'd have to do, once I knew an x value, is just multiply it by 4, instead of trying to plug it through all of these crazy calculator problems and making it more complicated. I've actually simplified it. Alright, let's look at inverse functions. Now we already know from experience in our chapter 2 and 3, mostly in chapter 3, how to write inverse functions. First thing you want to do is flip your x and your y. So x is equal to 8y, 8 to the power of y. Well, we know from our logarithmic property, again, lesson 1 should be on the note card, that log of base b to the power of y equals x. That means b to the x equals y. So the property rule tells us that 8, the log of 8, oops, I mean that way too big. This is a subscript, so it should be small. The log of base 8 of x is equal to y. So this would be my function. All right. For example B, step 1, flip your x and your y. Remember that natural log means the base is e. So this is going to be e to the x is equal to y minus 2. So then add 2. So e to the x plus 2 is equal to y. So a natural natural exponent equation here with a vertical shift of 2. Again, make sure you watch out for those parentheses. If you forget the parentheses, you end up with e to the x plus 2 is equal to y. And it's a slightly different equation, has a horizontal shift instead of the vertical shift, and you end up with a different graph. So watch your parentheses. This whole thing is equal to e to the x. Okay, so let's move on to graphing. Speaking of graphing. Alright, so before I start graphing, let's set up a couple of things. I want to show you the parent function that these were originally, and I'm going to show you they need to be reflected across the axis, the y equals x-axis to show the vertical. I'm going to draw the original exponential growth and decay functions in blue, and then I'll draw the logarithmic functions. So the original functions we dealt with last chapter were b to the x. So if b is greater than 1, then that meant that as x approached infinity, y approached infinity. And as x approached negative infinity, y approached 0, or whatever the k value was. So for exponential growth functions, these were, the domain was all real numbers, which some of you have noticed that if you draw an R with a little extra line in there, that means all real numbers. Or you can always just write out all real numbers. And then y values were greater than whatever the k is, in this case, 0. Notice that all your y's are greater than 0. Now if we take a look at what happens when b is between 0 and 1, these were what we called exponential decay functions. So as as x approached positive infinity, y actually approached 0. And then as x approached negative infinity, then you had y approaching positive infinity. So the domain is still the same. X is equal to all real numbers. And then y is still all the values that are greater than 0. Notice they're all above the y-axis or the x-axis. So all the y values are positive. That means greater than 0. Doesn't matter that it's a decay function. Decay function means it's approaching from the top, but it's still, all the y values are still greater. Alright, so let's take a look at what that means for us when we have our logarithmic functions. So again, switching the x and the y, we're going to end up with a point here. Now the main difference here is because we're switching the x and the y, we're actually switching the domain and range. So now, instead of your graph approaching a y value, approaching that x value of 0, now it's approaching the y value of 0, now it's approaching the x value of 0. So this time, your domain is affected by any changes to the x. So the domain are the x values that are greater than 0. It's no longer all real numbers. Notice it gets to x equals 0, and it stops. It doesn't go any further. And this time, the range is going to be equal to all real numbers. Because you have positive y, you have negative y, that's going infinitely in both directions. So that's the big change here, is that we have flipped our domain and range rules. So now, originally, our range was affected by the k value. Now, our domain is going to be affected by the h value. Let's take a look at what happens when it is the b is between 0 and 1. Notice that b is still positive, but it's between 0 and 1, so it's a fraction or a decimal. This time, kind of like the decay function, as y approaches positive infinity, then x is going to approach 0, or whatever the h value is, and then as y approaches negative infinity, x is going to approach positive infinity. So the domain, these are the x values. Notice that all of our x values are to the right of x equals 0, so that means x is greater than 0. And our range is all the possible y values, and notice that positive and negative infinity, so the range is all real numbers. Take a moment to copy this down into your notes so you can be able to refer back to it and really notice the differences between what's happening with the exponential functions in blue and what's happening with the other functions in red. the logarithmic functions. Okay, so now let's actually put this to practice, and we're going to graph a function. When we graph this, again, we don't really want to worry about what's going on with the x plus 1 minus 2. Let's just take a look at what happens when we have just the log base 3 of x. Now notice the base is 3, so we can't really use our graphing calculator. You can't really type this into your graphing calculator. So you might be thinking to yourself, oh my gosh, what am I going to do? Well, again, the idea is, remember that 3 to the y is equal to x. So we're going to treat this a little bit differently. Instead of giving x values and finding the corresponding y values, we're going to give y values and find the corresponding x values. So 3 to the 0 is 1, 3 to the first is 3, and 3 squared is 9. So we have 1 comma 0, we have 3 comma 1, and we have 9 comma 2. So here are those points right here on the graph. Going back to the function, we have an h value of -1 and a k value of -2. So that tells me, h tells me to shift to the left 1 unit, and then k tells me shift down 3 units. So there's my new point. To the left 1 and down 2. To the left 1 and down 2. So now I have my new points. I'm going to graph out the line, and as y approaches negative infinity, x is going to approach -1. So here is my new vertical asymptote. Notice it's the same thing as what your h value is. It's the domain. X is greater than -1. The range. The y values are equal to all real numbers. So you have those slight changes, very similar to what we did with the exponential functions, but switched because now we're talking about the inverses of the logarithmic functions. All right, so let's take a look at some sample problems. Go ahead and pause it here. I'm not going to dally too long since we're running out of time on our 15-minute time limit. So take a moment, pause here. There's a bunch of questions on simplifying, finding inverses, and graphing. And then when you're ready, press play to get the solutions. Okay, so here are your answers. Circle the ones you have questions about so we can cover them in class, and I will help you out as much as I possibly can. See you tomorrow.